My job can be pretty rough. So when I get home, I like to relax. I go to my backyard, sit on my lounge chair, and pull up a good physics book. You know, physics. A little inertia, a little mass, a little velocity. It helps take the stress of the day away. So what I suggest to you is when you're at home relaxing, you should pull up a good physics book. Physics. It's very smooth. Sports figures. Put your brain in the game.
Football, physics. Football, physics. What could physics possibly have to do with football? Well, that's the cool thing about physics. Physics has to do with everything. Physics describes the way our universe works, and a physics book is like an instruction manual for the universe. One of the most important and fundamental parts of physics are the laws of motion. Way back in the 1600s, an English guy by the name of Isaac Newton came up with a set of laws to define motion. He just called them the 3 laws of motion. Today we call them Newton's laws of motion. That makes sense, right? Well, these laws were a big deal back then, and they still are today. Newton's laws can tell you how to throw a pass back, how to block, how to plow through some big, nasty defensive lineman. This guy behind me is an object in motion. He's a big object. He's Jamal Anderson. He's a running back for the Atlanta Falcons. Last year, he went to the Super Bowl. And today, he's here to help us take a look at some Newtonian physics.
I am?
Yes, you are.
And it's gonna help my game?
Well, in football, there's motion and force, right?
Right, that's the whole game.
Well, that's Newton's whole thing, too. Motion and force. Go on for a pass. Okay, Jamal, let's talk Newton's laws of motion.
Okay, I remember the first one. An object at rest will remain at rest, and an object in motion will remain in motion.
Okay, that seems pretty simple. This football isn't going anywhere. I could stand here forever, and it's not going to move. Even though it's not moving, there are forces at work on the ball. Gravity is pulling the ball down, and the kicking tee is pushing back up. But these forces are balanced. And how do we know that they're balanced? Because nothing is moving. Unless something comes along to move it, that football isn't going anywhere. But if I do this, it moves, right? Because I applied an unbalanced force. An object will remain still until an unbalanced force comes along to change its velocity. But that's Newton's second law, and we'll get to that in a minute. Newton's first law also says that an object will remain in motion until acted upon by some other force. A football flying through the air doesn't remain in motion. Something changes its velocity. Now, according to Newton's second law, some unbalanced force must be acting on the ball.
Well, the force of gravity is pulling it down, so eventually it will hit the ground or get caught by a person, and that force stops it completely.
The resistance with air while it's moving slows it down too.
Right. Now, if I could throw this football into outer space...
Nice arm.
Once the football is free of the Earth's gravity and atmosphere, according to Newton's first law, it would keep going on forever, or until it encountered some unbalanced force, which is Newton's second law. Now, the tendency of a ball or an object to move or not to move is called inertia. Newton's first law is sometimes called the law of inertia.
Okay, I know this one. That's why linemen are so big, because a big player at rest is really hard to move because of his inertia.
Right, inertia is a function of mass. And when a big guy like you is in motion...
Well, my inertia keeps me in motion.
Right, you're hard to stop because of your inertia. An unbalanced force doesn't always mean moving and stopping. If it changes direction, it changes its velocity too.
Okay, like when I bounce off a tackler.
Newton's laws seem pretty simple. If nothing comes along, or no force comes along to affect an object, it'll keep doing whatever it was doing.
Yeah, the first law is not too bad.
Okay, the second law.
The second law is force equals mass times acceleration, right?
Right. Newton's second law deals with force that makes something move. Forces produce accelerations. It gives us a way to measure it. If I'm standing here and Chris plows through me, I move, right? And if I move, there must have been a force that affected me. An unbalanced force. Newton says so. Whether it makes you move or stops you, a force changes your velocity. And that's called acceleration. And thanks to Newton's second law, we can figure out how much force there was. And it was a lot. Believe me.
Let's go to Tom Jackson at the Sports Figures blackboard at the Shippingburg Area High School in Pennsylvania. Take it away, Tom.
Thanks, Jamal. I'm here with Miss Gould's physics class at Shippensburg Area High School in Pennsylvania. Today's NFL segment is based on ideas that they submitted for the Sports Figures NFL contest. Let's say it's your job to stop Jamal Anderson running downfield at full speed. You might think you were trying to stop a freight train. It takes a lot of force to change Jamal's velocity. And we can figure out just how much force thanks to Newton's second law. Force equals mass times acceleration. Let's say at top speed Jamal runs 100 yards in about 11 seconds. That's about 8 meters per second. If hitting the defender changes his velocity, stops him in half a second, then his acceleration is 16 meters per second squared. He stopped at 16 meters per second squared. Any change in velocity is an acceleration. His mass is easy, 234 pounds or about 106 kilograms. All we have to do is plug the numbers in to find out that this body in motion is going to take a force of about 1,700 newtons to stop. That might seem kind of backward, that we figure out the stopping force instead of Jamal's force. Newton's second law deals with acceleration, which is the change in velocity. We can't just take Jamal's speed coming downfield. The force is measured by how much and how fast the speed of his mass changes. Now, I don't know about you, but I don't want to be standing in the way when Jamal Anderson comes through. I'm Tom Jackson here with the Sports Figures blackboard in Shippensburg, Pennsylvania.
What happens when you throw the ball?
I apply force, and the ball gets accelerated.
What if you apply the same force and the mass is way bigger?
I'd get less acceleration.
And if it's way smaller?
The same force would make more acceleration.
I got it! If a car hit me at 20 miles per hour, I don't have the force to stop it. That'd be bad. But if an insect hits you at 20 miles per hour, that wouldn't be bad. Unless, of course, you swallowed it. Yeah. Now, I can apply a small acceleration to a bigger mass, the car, or a big acceleration to a smaller mass, the insect. My force won't stop the car, but it will stop the insect. Now, if the insect is traveling at 10,000 miles per hour, now that insect needs a bigger force, needs a bigger acceleration, needs a bigger change in speed to stop it.
Okay, I got it. When I'm coming through the hole, the lineman applies the force.
Right, and his force is going to change your speed.
All right, and if the force is big enough, the change in speed will be enough to stop me, bring me down to a speed of 0.
Newton's second law is that simple.
Okay, I got it.
All right, let's move on to the third law.
Everybody knows this one. For every action, there was an equal or opposite reaction.
He's right. When I hit this tackle dummy, I apply a force to the dummy. Not this one, this one. So why does my shoulder hurt? It's because the dummy applied an equal force back on my shoulder. So the harder I hit this thing, the more it's going to hurt. It's going to give me back everything it gets. It has to. Newton says so. Mark, what happens if you push Billy?
If I push him, he's gonna move.
Okay, that's Newton's second law. You apply a pressure or force to an object, and it's going to accelerate in the direction of that force. Let's try it. What happened?
I move too.
Right, because when you applied a force, there was an equal and opposite force against you, so you moved. That's Newton's third law.
Forces always come in pairs.
Thanks to Newton, we know that anywhere in the universe that we apply a force, there's an equal and opposite force in return. The Earth is applying a force on me, gravity. It's accelerating me down. But there must be an equal and opposite force. I'm applying a force on the Earth and accelerating it up. It's pulling me down, and I'm pulling it up. But you didn't see the Earth come up toward me, right? Because the forces of gravity on me, a small mass, gives a big acceleration. Now, the same forces on Earth, a huge mass, gives a tiny, unobservable acceleration. It's hard to imagine, but it's true. As gravity pulls you down, you pull the Earth up. Kind of like this. Only way, 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 way smaller. If what Newton says is true, how could I ever move this truck? When I push the truck, I apply a force, and the force that I apply moves it. When the truck applies an equal force back on me, shouldn't I move? It's the same in football. The force of one lineman is equal to the force of the second lineman. Shouldn't they both accelerate and nobody get anywhere? So how is that possible? Is Newton wrong? So what's going on here? The forces are both equal and opposite.
But you said that force is a function of mass and acceleration.
Right.
So even if the forces are equal and opposite, it must be an unbalanced force because the car moved.
The only force on the truck is my force. The wheels make it easier to move. But the equal and opposite force of the truck is not the only force on me. The friction between my shoes and the ground is another force. I don't move because there are two forces on me, the car and the friction with the ground. The receiver only has the horizontal force of the defensive back on him, so he accelerates horizontally. The defensive player has an equal force on him that should push him back, but friction with the ground is another important force on him. If I'm on skates and I try to push the truck, watch what happens. Okay, here's what's happening. Let's take a look at Newton's second law. Force equals mass times acceleration. If I try to push the truck like this, it won't work, right? That makes sense, because the force that I'm using is exactly the same amount of force that's back on me, and my mass is much smaller than the truck's, so I move.
Wait a sec. How could you ever push a car?
The same way I push you. Okay, here's the deal. When I wear my sneakers, there's a lot more friction between myself and the ground. It's almost like I'm nailing my sneakers to the ground. And when I push the truck, my mass is actually greater. The mass of the Earth is what makes me able to push the car. The force is greater because of the traction. I can get my legs into it. Now, the greater force moves the truck and doesn't seem to accelerate me. Without a connection to the Earth's mass, I can't accelerate you much because your mass is bigger. And the force that I apply is less.
That's why traction to a football player's shoes is so important. It's the traction that allows the Earth mass to get underneath us and lets our leg muscles get into the game.
Right, so if you're going to play football, you want to keep your feet on the ground. Check this out. If players with roughly the same mass and acceleration hit in midair, their equal and opposite forces do cancel out and they both stop. But if one player is pushing off the Earth and the other isn't, even though their masses and accelerations are similar, this guy's gonna lose some potential yardage.
Okay, I got it. The force on the car and the force on you are equal. But your mass is greater than the car if you attach to the Earth with friction. The car accelerates and you don't,
Almost. Actually, I do accelerate a bit.
but you didn't go backward.
I can't have zero acceleration because my mass times zero would give us a force of zero. And we know that that's not true. When I push off the Earth's mass, the Earth moves back a little bit too.
Really?
Yeah.
The Earth moves?
A tiny bit, yes.
No way.
Look, when I jump, the force pushes my mass up, and it pushes the mass of the Earth away from me. Try it.
You mean to tell me, so when we play, the Atlanta Falcons play, and Jamal Anderson's running the ball, that the Earth has to move?
It does, but the mass of the Earth is so great, the acceleration can't be felt. But it's there, and we know it's there, thanks to Isaac Newton. Let's say you had to design a video football game, and you had to figure out what would happen if Jamal Anderson collided with John Randall. Ouch. With Newton's laws of motion, you could figure it out. When Newton came out with his 3 laws back in the 1600s, they caused quite an earthquake because no one had defined things quite like this before.
You guys came up with this idea. Tell us what we learned.
Then an object will keep doing whatever it was doing, stay still or keep moving, until an unbalanced force acts upon it. That's the object's inertia.
Inertia is mass. The more mass something has, the greater the force has to be to stop or move it.
Moving or stopping it is an acceleration.
That's Newton's second law. Force equals mass times acceleration. The faster the mass moves determines how much force it takes to stop it.
And that for every force applied, there's an equal and opposite force.
Any object that experiences a force is accelerated by that force, but sometimes you can't see or feel the acceleration, like the Earth, because the mass is so large.
Very good. Miss Gould, take a bow.
We'd also like to thank Jamal Anderson and the Rye High School students Billy, Mark, and Chris for helping us today on ESPN's Sports Figures, Newton's Earthquake. Ooh. Ooh.